Welcome back, ladies and gentlemen. Today we're going to tackle 7.3 similar right triangles. I want to give you a fair heads up warning here that this particular section is a little bit more difficult than average, so I would wholeheartedly recommend just sitting down and taking proper notes and maybe reviewing, rewinding uh, this topic to see that you fully understand the topics before you get into class. As always, on the screen, you'll see your exit question that you'll be asked on the exit form. I'd like to start off with thinking about a very simple example. Here's a right triangle. It's got one label angled, and the only thing special that I've done is I've oriented it so that the right angle is up at the top and the hypotenuse is down at the bottom. So we could refer to the hypotenuse as the base here. Now, what I'm going to do to start our discussion today is I'm simply going to construct an altitude. I'm going to construct an altitude that goes through the right angle and connects to the hypotenuse. Just like that. I'm also going to add point D in there and label it. Now, if you start thinking about similarity here, you might notice some interesting things. First, it's important to realize that we've now taken the large original right triangle and we've split it up into two smaller right triangles. From there, if we wanted to start talking about similarity, we would have to prove that at least one more angle is shared in common between the small and big and the medium and big. And it turns out this is not too difficult of a task because we can say, hey, look at that. There's a 90-degree angle, there's a 90-degree angle, and there's a 90-degree angle. So all three, small, medium, and large right triangles share a 90-degree angle, which means that if we can just show one more they share, then they would be similar. All three of them would be similar. So let's take a shot at doing that. Take a look at angle B over here. Angle B over here is shared with the smallest of the three triangles, CDB, and the largest of the triangles, ABC. And it just so happens, since it's shared and not the 90 degrees, we now have our two angles that we need to prove similarity. So the small triangle is similar to the largest triangle. Likewise, I can perform the exact same argument for angle A. I have angle A that's being shared between the medium triangle and the large triangle. Therefore, by the double A similarity postulate, these the medium triangle is similar to the large triangle, which means that once I split that right triangle into two smaller right triangles, that not only are both the triangles that I split it into similar to the original, but then they're also similar to each other. In other words, the similarity is transitive. And it looks a little something like this. So if you take an original triangle and split it into, or draw an altitude, you will split it into three similar right triangles. And once we've proven that all three of these triangles are similar to each other just by simply dropping an altitude through that right triangle, right angle, we can now write any proportion statements for any combination of these three so long as we're conscientious of which parts correspond to each other. So let's jump right into an example. I know I slipped and I went too far, so you might have seen it already, but here is our example for the day. It's a swimming pool, and I'd like to know how deep it is. And you can see that this swimming pool is constructed so that it's got a rectangular cross section that is 48 inches deep, but then it's got this deep end that starts in the middle somewhere, slopes down, and also the deep end slopes down at some angle. So we've drawn this imaginary line to coincide with the shallow end, and we know that that's 165 inches, but we don't know how deep that is. We are also able to measure this distance and the distance of this slope here. So I'd like to know h. And you might notice that, hey, you've got this same situation where you have a right triangle being split with an altitude. So therefore, we've got three similar right triangles. And the question is, where the heck do you start on this problem? Well, these drawings become quite complicated because you're not only talking about three triangles that are all similar to each other, they all have corresponding parts, and they're all rotated differently. So what you have to become good at is discerning which triangle is which and which parts correspond to which parts of all three triangles. So my best piece of advice for you today is to be able to take one of these drawings and deconstruct it into each of the three individual triangles, the small, medium, and large. Orient them in the same way and label as much as you can, accurately, of course. So let's try to figure this out, just trying to figure out which triangles are which. Let's start with a big triangle, since that's the most obvious, I think. Let's go RST, okay? We'll highlight it here, we'll bring it over here, and then we'll put everything on there that we know. And actually, we know an awful lot about RST. We know that its hypotenuse is 165, this leg is 152, this leg is 64. I suppose the next thing to do would be the medium-sized triangle. Now, I not only want to highlight it, but I also want to rotate it so that it is oriented the same way as RST so that I can more clearly see the corresponding parts to it. So I'm going to take RTM and I'm going to rotate it so it's kind of hypotenuse or belly up, just like RST is, and label as much as I can again. And we know that the hypotenuse for RMT is 152, so that should be up on top. And we know one of its legs is H, and that's really important because that's what we want to get after. And then we can do the same thing for the small one, and we can see that the hypotenuse is 64 this time, so that's going to be the top side once we orient it and label it again. Now notice that both the small triangle and the medium triangle contain H, which is what we're interested in. And what's really helpful is RST has all three of its sides labeled. Now through theorem 7.4, we know that all three of these triangles are similar to each other. And like I was saying before, similarity is indeed transitive. So if RST is similar to RTM and RTM is similar to TSM, then by the transitive property of similarity, RST is similar to TSM. You don't need to know that, but cool fact anyways. You might need to know that in the future, who knows? Anyway, once we've gone through all that work to draw and label and orient all three triangles in the proper way, it's very, very easy to see which parts correspond to which parts. So in my mind, I look at H, I really want to know what H is, so I'm going to look for another triangle where H I know something about, and this one is labeled as H as well. Well, this corresponds to that piece, and I don't know anything about that piece. That doesn't have a label. And this corresponds to that piece, and bam, I've got a number. So if I can just figure out another pair of corresponding parts, we should be good. So I look for maybe this leg, which I know nothing about, so that's no good to me. So I got to go with this hypotenuse. And it just so happens that this hypotenuse is also labeled over here on this triangle. Now I didn't go over here because this doesn't help me because that side isn't labeled for me. So I got to use 152 to 65 and H to 64. So I'm going medium to big and medium to big. And if you do that, it looks like this. Okay, so I did, yep, medium to big and medium to big. And once you get that proportion, simple cross products and solve. Except we've been enforcing the idea of exact answers, and if you do that, you get something really gross. So let's just call it 59. 59 inches. Perfect. Look at that. It's missing a label. Oh well. You know what? It has a label now because I said it verbally. Moving on. That was 59 inches. That was just for the deep end. That was right there to there. But remember, we had water above this. In fact, we had 48 inches of it. So to finish the problem, we just got to tack on that 48 inches to the answer that we just got, which is pretty easy if we approximate it at 59 inches. Or if you really wanted to go all out and give an exact answer, it would look something like that, which I think looks really ugly. The point is that you couldn't even do that with like bar notation on decimals because I think this decimal has a repeating pattern that's like an insane number of digits long. So you'd have to like have, who knows, like 25 digits with a bar over it. And that would be a pain. So uh, estimating is nice sometimes, or this ugly looking mixed number works too. Okay, the next item of business is going to be talking about this same drawing where we took a right triangle, split it with an altitude, and we got two smaller right triangles. Now this time I'm going to orient it just the smaller right triangle just a little bit differently to point something out. Because we know that these three triangles are similar, and I'm just going to talk about the red and the blue one, that means that if I take this length AD and divide it by length CD, I should get the same number, though not the scale factor, as I would if I took CD and divided by DB. So in other words, if I took long leg to short leg and long leg to short leg, because I know those are similar, they should share the same proportion there. Okay? And if we do that, if we label it, even in general, we get this proportion set up. What's really interesting about this proportion that I've written here is that the means are identical. And this was the generic case, so it doesn't even matter what those numbers are, but they will always be identical. And you'd say, well, then CD must be pretty important. And we look at CD here, and it's a shared side between these two triangles. And even more important, CD is our altitude. And the question is, well, what makes CD special? We look down at this proportion equation and it ought to look really familiar. That is basically saying that CD is the geometric mean of AD and DB. So that means that if I took the length of AD times the length of DB and then took the square root of that, I would get the length of CD. Crazy concept, crazy thing to remember, obscure thing to remember, but helpful when you're trying to figure out these weird geometry problems. So what you do need to know, just general concept, that length right there is the geometric mean of that length and that length. Stated a little more complicated and or maybe a little bit more eloquent, I don't know. Uh, Same thing. BD is to CD as CD is to AD, meaning that CD is the geometric mean of the length of BD and the length of AD. Even even more obscure is our next theorem for the day, 7.7. And there are all the highlighted segments that are involved there, just color coding things. Uh, I'm not going to talk about this one a whole lot because I haven't really thought of a good way to make sense of it or to help you memorize it. But since it's written down on your theorem sheet, the things that you need to be aware of is that when you have this right triangle being split with an altitude, is there are several proportions that can be written from it. And two of those proportions are here. Notably, you can associate AC as a geometric mean between AB and AD, and you can also associate CB as a geometric mean of AB and DB. So not only is CD a geometric mean, but so can be the legs of the original largest right triangle. Here's our best shot at color coding things. Okay, so CB is the geometric mean of that and the total distance of the hypotenuse. And if we clear everything out and do that again, we got AC is the geometric mean of AB, the whole hypotenuse, and AD, the partial hypotenuse. Really difficult to memorize, but just please be aware of those proportion statements that you can write if you need to figure out some unknown length. Okay, let's do one last example quickly. I know this video is getting long here. So here's the known information. What we're going to do here is we're going to do something kind of weird. We're going to put a square piece of cardboard up against our eyes, and we're going to sight down that square piece of cardboard in such a way that if I sight down the top edge of the cardboard, I see the top corner of the gymnasium, and if I sight down the bottom edge of the cardboard, I see the floor to wall intersection. Then I'm going to have somebody measure how tall my eyes are, and I'm going to have someone measure uh, how far my eyes are from the wall, and hopefully we'll be able to figure out how tall this gym is. Okay, so we're going to use the first part about the geometric mean. So this is the geometric mean of this and this, which means that I can set up a proportion where that is the lower left and upper right diagonal, and W and 5 are the extremes. So that can be put in my proportion equation 2 times, and these two numbers fill in the remaining blanks. So the proportion setup, if you know what you're doing, is very easy. So again the proportions involved. So the proportion setup, we put 8.5 in the means and we put W and 5 in the extremes. And it looks like that. And then from there it's cross products and solve again. So we get W equals 14.5. So that part's 14.5 plus 5 feet tall for a total of 19.5 feet for the ceiling height. As you can imagine, there's a lot of ways to write these proportion equations based on 7.7 and 7.6 in combination, and even 7.5 for that matter. So be aware of how many different proportion statements you can write, and do your best to keep them straight. Just always reference a theorem to figure out if you're doing something right. Make sure of it. Here's your assignment. I will see you next time.